Every choice you make might be spawning an entirely new universe. We are about to explore 30 of the most incredible theories on quantum timelines, a concept that shatters our basic understanding of reality, existence, and even time. This journey will completely reshape how you see your own place in the cosmos. We will uncover whether dinosaurs still walk in a parallel world, and if your consciousness is actively creating reality. By the end, you will hold a new framework for understanding everything from the Big Bang to the nature of your own thoughts. What single mystery about reality are you most eager to unravel? The very fabric of reality might be an infinite tapestry of branching paths. This is the core of the many worlds interpretation, a theory proposed by physicist Hugh Everett in the 1950s. He suggested that every single quantum event, every tiny decision, does not resolve into one outcome. Instead, the universe splits, creating a new, fully realized timeline for every single possibility. Think of it like a choose-your-own-adventure book, but on a cosmic scale. At every choice point, you do not simply turn to one page. The book itself duplicates, creating a new, complete volume where every alternative story is being lived out simultaneously. In one universe, you took that different job offer. In another, you never met your best friend. And on a grander scale, there is a universe where the asteroid missed Earth and dinosaurs still rule the planet. This idea was born from a desire to solve one of quantum mechanics' greatest puzzles, superposition, where a particle can exist in multiple states at once until it is observed. The many worlds theory suggests it is not that the particle chooses a state when we look. It is that we, the observers, are split along with it, each version of us perceiving a single, definite outcome. This means there is no single, definitive timeline. There is only an ever-expanding multiverse of every possible reality. But the idea of endless branching universes is not the only way to understand the quantum world. There is a much older and for many decades the dominant explanation. It is called the Copenhagen Interpretation, championed by physicists like Niels Bohr and Werner Heisenberg. In this view, reality does not split endlessly. Instead, it remains fuzzy and undefined, a cloud of potential, until the very moment it is observed. Only then does it snap into a single, concrete reality. This moment is known as the collapse of the wave function. It is the act of looking that forces possibility to become fact. To make this bizarre idea tangible, physicist Erwin Schrödinger proposed a famous and famously macabre thought experiment. He asked us to picture a cat sealed inside a box. With the cat is a tiny, radioactive atom. There is a 50% chance this atom will decay within 1 hour. If it does decay, it will trigger a mechanism that releases a poison, killing the cat. If it does not decay, the cat lives. Now, according to the strict rules of quantum mechanics, until we open the box and look inside, that radioactive atom exists in a superposition. It is both decayed and not decayed at the same time. And because the fate of the cat is tied directly to the state of the atom, the cat itself must also be in a superposition. It is both alive and dead, a ghostly mixture of two states until the very moment an observer peers inside. That single act of observation collapses the wave function, forcing the universe to choose one outcome. The cat is either definitively alive or definitively dead. Schrödinger intended this as a critique to show how absurd he found the idea of a cat being both alive and dead. Yet the experiment perfectly illustrates the core mystery of the Copenhagen interpretation. The observer is not a passive witness, they are an active participant in creating reality. This places human consciousness, or at least the act of measurement, at the very center of the quantum world, a profound and unsettling idea that continues to spark debate today. Yet there is a third path, one that rejects both the ghostly cat and the splitting worlds. The de Broglie-Bohm theory offers a radically different vision, a universe that is not random, not branching, but deeply deterministic. Here, every particle has a specific position and a definite trajectory at all times. There is no blurry cloud of probability. The apparent randomness of quantum events is an illusion, a trick of perception. So what guides these particles on their precise paths? A hidden reality known as the pilot wave. Think of a tiny boat being pushed across a choppy lake by invisible underwater currents. The boat has a real, physical location at every moment. Its path seems erratic and unpredictable to us on the shore, but that is only because we cannot see the complex waves guiding it. In this theory, the particle is the boat and the pilot wave is the hidden current, orchestrating every movement with perfect, predetermined order. This means the universe has a single, non-branching timeline. It is a cosmos governed by precise, albeit hidden, laws where everything unfolds from a fixed starting point with clockwork certainty. The profound implication is that free will itself might be an illusion, a story we tell ourselves while being carried along by these invisible, guiding waves. Yet this deterministic universe is just one possible answer. Another theory takes the many worlds concept to its most personal and unsettling extreme. Quantum immortality suggests that your conscious experience is forever bound to timelines where you continue to exist. Imagine you are part of a terrifying experiment. You are placed in front of a device that is triggered by a random quantum event, like the decay of a single atom. There is a 50% chance the device will fire a deadly bullet and a 50% chance it will do nothing. You pull the trigger once. In many branches of the multiverse, the device fires and that version of you dies. But from your own first-person perspective, what do you experience? You only find yourself in the timelines where the gun did not fire. You try again and again and again. Each time, countless versions of you perish, but your stream of consciousness only follows the path where you miraculously survive. To you, it would seem as though you are impossibly lucky, defying astronomical odds with every pull of the trigger. This thought experiment, known as quantum suicide, implies that from your own subjective viewpoint, you could never experience your own death. You would always find yourself in a branch of reality where you continue living, no matter how unlikely the escape. This leads to a bizarre philosophical conclusion. You might, in a sense, be immortal, not because your body is invincible, but because your consciousness constantly hops to a timeline where it persists. This idea forces us to confront the nature of existence itself. Is our life just a single, linear story, or is it one thread in an infinite tapestry where our awareness is forever tied to survival? While purely theoretical and deeply controversial, it challenges our most fundamental assumptions about life, death, and the very fabric of our reality. This cosmic branching of timelines might not be limited to our own universe. The very mechanism that gave birth to our cosmos could have spawned an infinite multiverse from the very start. This idea stems from the theory of cosmic inflation, a period of unimaginably rapid expansion in the first fraction of a second after the Big Bang. According to some models, this inflation did not stop everywhere at once. Instead, it is eternal. While it ended in our local patch of reality, forming our observable universe, it continues forever in the space beyond, a process called eternal inflation. Think of a vast, bubbling pot of water that is always boiling. Our entire universe is just one single bubble that formed and stabilized within that endlessly churning foam. And we are not alone. New bubbles are constantly nucleating out of the inflating background, each one a brand new universe disconnected from our own. This is the inflationary multiverse. Within this grand cosmic foam, each bubble universe can have wildly different properties. The fundamental constants of physics, the strength of gravity, the number of dimensions, even the very nature of time could be completely different from our own. In one bubble, gravity might be so strong that stars form and burn out in an instant. In another, time might not flow in a single direction as it does for us. Our universe, with its specific life-permitting laws, is not special or fine-tuned. It is simply one possibility among an infinite number, a single lottery ticket drawn from a cosmic hat of endless variety. The quantum fluctuations that seeded the galaxies in our universe are the very same mechanism that seeds these new bubble universes in the greater multiverse. This connects the quantum weirdness of the small scale directly to the ultimate fate of the cosmos, suggesting that our entire reality is just one branch on an infinite, ever-growing tree of existence. Our journey into quantum timelines now confronts a vision of reality where time itself is an illusion. The block universe theory proposes that past, present, and future are not a flowing river but a timeless, four-dimensional sculpture. In this model, the entire history of the cosmos is laid out at once, a single, unchanging block where every event that has ever happened or ever will happen exists eternally. Your birth, your life, and your eventual death are all equally real and permanent parts of this structure. The feeling of time passing, of a present moment moving forward, is just a peculiar feature of our consciousness, a kind of mental spotlight scanning across a film reel that is already complete. This idea emerges directly from Einstein's theory of relativity, which showed that the flow of time is not absolute but depends on your motion and gravity. If you could step outside the universe, you would see all of time spread out before you, from the Big Bang to the farthest future, frozen in a single, breathtaking instant. This radically challenges our sense of free will. If the future is already written, then our choices are not creating new paths but simply revealing a course that was always there. From this perspective, the quantum probabilities we explored earlier are not signs of genuine randomness. They are merely a consequence of our limited, slice-by-slice view of the grand, predetermined block. We are like readers discovering a story one word at a time, unaware that the entire book is already finished. But what if the future is not just written, but is actively reaching back to shape the past? The transactional interpretation offers this mind-bending possibility, proposing that quantum events are not random collapses or branching paths, but a kind of cosmic agreement. In this view, every particle interaction is a deal brokered through time. When an event occurs, like an electron being detected at a specific location, it sends an offer wave forward through time. But it also sends a confirmation wave backward into the past. It is only when these waves from the future and the past meet and reinforce each other that a definite reality is settled. This moment of agreement is the handshake that seals the deal. Think of it like placing an order for a custom-made item. You, in the present, send your request forward. The workshop in the future receives your order and sends back a confirmation slip through time, saying your item is ready. The transaction is only complete when your original request and the future confirmation meet in the middle, locking the event into place. This introduces the staggering concept of retrocausality, where effects can precede their causes. The future outcome of an experiment could, in a sense, reach back and guide the setup of that very experiment, creating a single, self-consistent causal loop. This offers a potential escape from the weirdness of both the Copenhagen and many worlds views. There is no mysterious collapse triggered by observation, and no need for an infinite number of splitting universes. Instead, we have one timeline, but it is a timeline where the flow of cause and effect is not a one-way street. It is a grand, interconnected dance where the future and the past are in constant conversation, working together to build the solid reality we perceive in the present moment. This idea that observers create reality finds its ultimate expression in the participatory anthropic principle. Proposed by physicist John Archibald Wheeler, it pushes past the notion that we simply collapse possibilities. It suggests we are essential players in a cosmic drama, that the universe only comes into being because we are here to observe it. Wheeler used a powerful metaphor to explain this, which he called the game of 20 questions. Imagine playing the game but with a cosmic twist. You leave the room while the others secretly choose a word. You return and begin asking yes or no questions to guess it. The answers are consistent, and after 20 questions, you triumphantly declare the word is cloud. But then the others reveal a secret. They had not agreed on a word at all. Each person simply gave a yes or no answer that was logically consistent with all the previous answers, without any final goal in mind. The word cloud only emerged from the sequence of your questions. In Wheeler's view, the universe is like that. It is not a pre-existing, fully formed entity. It is a vast, amorphous cloud of potential that only takes on definite properties when we, the participants, ask it a question through our experiments and observations. Our measurements are not revealing a hidden reality. They are literally bringing that specific reality into concrete existence from a sea of what might be. This links our consciousness directly to the fabric of reality, giving it a role of profound importance. We are not just accidental tourists in a ready-made cosmos. We are the architects collaboratively building the universe moment by moment through the very act of perception. This carries a staggering philosophical weight. It means the specific timeline we experience, with all its history and laws, is not the only one that could have been. It is the one we have collectively chosen, or rather, summoned into being, through an endless chain of observations stretching back to the first conscious beings. The universe, in a very real sense, needed us to come alive. The solid world you touch and see could be a magnificent illusion, a cosmic projection with no more depth than a hologram on a credit card. This is the breathtaking claim of the holographic principle, a theory that reimagines the very nature of space itself. It proposes that our universe, with its three sprawling dimensions of height, width, and depth, is not fundamental. Instead, it is a holographic projection of information encoded on a distant, two-dimensional surface that surrounds us. All the stars, planets, and people are akin to the rich, three-dimensional image that seems to float above a flat, etched piece of plastic. This radical idea did not emerge from pure speculation. It was born from the study of the most enigmatic objects in the cosmos, black holes. Physicists discovered a deep puzzle. The amount of information, the total entropy that can be stored within any volume of space, is not proportional to its volume as you might expect. It is proportional to the area of its boundary. Think of it like this: the total data that can fit inside your entire house is not determined by the cubic footage of all its rooms. It is determined by the square footage of the outside walls. This is a profound clue that the true, fundamental reality might be happening on that two-dimensional surface, and our three-dimensional world is just a translation of that data. This principle finds a home in string theory, where it suggests that our universe could be a hologram projected from the boundary of a higher dimensional space. What does this mean for our quantum timelines? If our reality is a projection, then every possible event, every branching history we have discussed, is not happening within the volume of the cosmos. All those potential histories are simply different sets of information encoded on the cosmic boundary. The infinite multiverse becomes a vast library of data written on a flat, two-dimensional shell. This elegantly solves one of physics' greatest challenges, uniting gravity with quantum mechanics. In this view, gravity is not a force like the others. It is an emergent phenomenon, a consequence of the holographic projection. Just as the illusion of depth emerges from a flat hologram, we are not living in a universe. We are living in a cosmic data stream, and every moment of our lives is one line of code being read from the ultimate hard drive. Our holographic projection finds its mathematical soul in the vibrating threads of string theory. This framework suggests that the most fundamental components of reality are not point-like particles but unimaginably tiny, one-dimensional loops of energy. Their different vibrations, like the distinct notes on a violin string, give rise to every particle and force in existence. But for these strings to produce the rich symphony of our universe, they require extra dimensions of space, curled up into shapes so small we never perceive them. This is where the landscape multiverse unfolds. The specific way these extra dimensions curl determines the laws of physics for a universe, dictating the strength of gravity and the mass of an electron. String theory does not predict one unique way for this to happen. Instead, it predicts a staggering number of possibilities, a cosmic landscape of perhaps 10 to the 500 different vacuum states. Each of these stable configurations is a unique set of physical laws, a different possible universe. Our cosmos, with its life-permitting constants, is just one fertile valley in this vast mountainous terrain. The eternal inflation we discussed earlier becomes the engine that populates this landscape. As new bubble universes nucleate from the inflating void, their extra dimensions snap into a random, stable configuration. Most of these universes would be sterile voids where atoms cannot form or forces are too weak for structure. But in an infinite multiverse, every possible set of laws, every conceivable quantum timeline must manifest somewhere. A universe where dinosaurs never went extinct is not just a different history. It is a different physical reality, a bubble where the strings themselves vibrate to a different tune. The profound challenge and the major criticism of this idea is its testability. If every possible universe exists, the theory can explain anything but predicts nothing specific about our own. We are left with the haunting possibility that the ultimate nature of reality may be forever beyond the reach of our experiments, a beautiful mathematical symphony playing in a cosmos we can never fully see. What if the quantum weirdness we have been exploring is not a feature of reality, but a clever design choice? The simulation hypothesis asks us to consider that our universe, with its infinite branching timelines, is not a fundamental reality at all. It could be an advanced computational construct, a simulation running on a computer of unimaginable power in some higher base reality. Philosopher Nick Bostrom formalized this possibility, arguing that at least one of three propositions must be true. Either civilizations like ours go extinct before reaching a post-human stage capable of running such simulations, or they have no interest in running ancestor simulations, or we are almost certainly living in one. If a civilization ever reached the technological maturity to create vast, detailed simulations of conscious beings, then the number of simulated minds would vastly outnumber the real ones. Statistically, we are more likely to be among the simulated. From this perspective, the strange rules of quantum mechanics start to look less like fundamental laws and more like efficient programming. Quantum randomness could be a computational shortcut. Instead of calculating every single particle in every single branch of the multiverse, which would require infinite processing power, the simulation only renders the specific timeline an observer is experiencing. The apparent collapse of the wave function is not a real physical event. It is the program deciding which outcome to display to the user, saving precious computational resources. All those other potential timelines in the many worlds view are not real parallel universes. They are merely potential states in the code, branches that exist only as unrendered possibilities. This even reframes the fine-tuning of our universe. The specific physical constants that allow for life are not a cosmic accident. They are the chosen parameters of the simulation set by its programmers. The very fact that we are here to observe it is a product of that initial configuration. Your entire life, your memories, and your sense of a linear past could be part of the data stream generated moment by moment. This idea forces a profound and unsettling question. If we are in a simulation, are the programmers watching, or is this a forgotten server running in a cosmic basement? And if our reality is programmed, what glitches in the matrix might reveal the code beneath the illusion? Yet the quantum world constantly leaks into our own, and this very leakage may be what builds our solid reality. Decoherence offers a powerful explanation for why we do not see cats that are both alive and dead, or tables in two places at once. It describes how a fragile quantum system, like Schrödinger's cat in its box, loses its quantum magic when it interacts with its surrounding environment. This environment is not a passive backdrop. It is a bustling sea of photons, air molecules, and radiation, all constantly bumping into things. When a quantum object in a superposition interacts with even a single photon from this sea, that photon becomes entangled with it. The photon effectively carries away a piece of information about the system's state. This process happens almost instantly, with trillions of particles all interacting at once, rapidly copying and scattering the quantum information into the wider world. Think of it like trying to keep a secret in a crowded, noisy room. You whisper a message to one person, but they immediately turn and whisper it to someone else, and within seconds the entire room knows. The secret is no longer just yours, it has become a public fact. In the same way, the quantum superposition is no longer a private affair between a few particles. Its information has been broadcast, copied, and scrambled into the environment. From our perspective, the superposition seems to vanish. The system appears to snap into one definite state, not because of a mysterious collapse, but because we can no longer see the whole picture. We are like someone who only hears one fragment of the whispered secret. We only perceive one of the many possible outcomes, and the others become effectively lost in the environmental noise. This provides a physical mechanism for the emergence of the classical world from the quantum fog. It explains why we experience a single, stable timeline, not a blur of possibilities. Our reality is not a single thread. It is the one thread we can still follow clearly after all the others have frayed into the background chaos of the universe. Decoherence does not create multiple worlds, but it does explain why we are permanently stuck perceiving just one. This symmetrical vision of time suggests that our present moment is a dialogue between two powerful voices, one from the past and one from the future. The two-state vector formalism is a quantum theory that takes this idea literally. It proposes that any quantum object is not described by a single wave function evolving from the past, but by two. One wave function comes from the past, as we would normally expect, carrying the history of how the system was prepared. But a second, equally important wave function comes from the future, defining the final state the system will be measured to have. The present is the delicate overlap, the point where these two waves meet and agree on what is happening right now. Think of a relay race where the baton is the present moment. It is not just passed forward from the starting line, it is also being pulled from the finish line. The runner in the middle, the now, is where the push from the past and the pull from the future find a perfect balance. This makes every quantum event fundamentally time-symmetric. The probabilities we calculate are not about what might happen, but about what must happen to ensure a consistent story is told from beginning to end. Our timeline, under this view, is not a path being carved into the unknown. It is a completed loop, a story where the first and last pages are written together, and every chapter in between must logically connect them. This offers a radical new take on probability and even predestination. The famous quantum randomness, where an electron seems to choose a path at random, is not random at all. It is the only possible outcome that satisfies both the initial setup and the final fixed result. The universe is not exploring every possible branch. It is simply finding the one route that connects its starting point to its ultimate destination. Are our choices free, or are they simply the necessary steps in a cosmic narrative that is already whole from beginning to end? The environment itself acts as a ruthless editor, selecting which quantum possibilities become our solid reality. This is the essence of quantum Darwinism, a theory that applies a principle of natural selection to the quantum world. It proposes that not all quantum states are created equal. When a system interacts with its environment, some states are fragile and get quickly scrambled into noise. Others are remarkably robust. They can be copied and spread to countless particles in the surroundings without being destroyed. These stable states are the fittest, and they are the ones that survive. Through a process akin to Darwinian evolution, the environment selectively amplifies these specific states, making them objective facts for any observer to see. Imagine a single drop of ink falling into a glass of still water. At first, the ink swirls in a unique, unpredictable pattern, but quickly it spreads and stabilizes, creating a uniform, faintly blue solution. Anyone who looks at the glass sees the same thing: blue water. The countless other possible, intricate patterns the ink could have formed were fleeting and unstable. They were not fit enough to be copied and communicated to the entire environment. Only the final, stable state of blue water achieves objective reality. In our quantum timeline, this means the world we perceive is not a random slice of the multiverse. It is the one where the quantum information has been most successfully replicated and broadcast. The chair you are sitting on appears solid and in one place because its quantum state has been redundantly copied into the trillions of photons bouncing off it and the air molecules colliding with it. That specific information has proven itself the fittest, outcompeting all other potential states to become the consensus reality we all share. This suggests our timeline is not chosen by our consciousness, but by a cosmic process of environmental selection, where only the most stable and communicable quantum data gets to define the world we all agree upon. A single thread of quantum entanglement might be a physical bridge in the fabric of spacetime itself. This is the astonishing claim of the ER=EPR conjecture, a radical idea born from the frontiers of string theory. The cryptic name comes from two of physics' most famous concepts, Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement. For decades, these were thought to be completely separate phenomena. Wormholes or Einstein-Rosen bridges are hypothetical tunnels through spacetime, shortcuts connecting two distant points. Quantum entanglement, the EPR part, is that spooky connection where particles instantly influence each other regardless of distance. This new conjecture boldly states they are not just similar, they are two different descriptions of the exact same thing. Every pair of entangled particles is not mysteriously linked. They are literally connected by a microscopic wormhole, a bridge so tiny it is far beyond our current ability to detect. This means the entire quantum realm could be woven together by an unimaginably dense web of these spacetime tunnels. Think of the cosmos not as a smooth, empty void, but as a cosmic sponge, riddled with countless microscopic passages that instantly connect every corner of reality. This has a staggering implication for our quantum timelines. If two entangled particles are linked by a wormhole, then perhaps every time the universe branches in the many worlds interpretation, these tiny bridges form, connecting the new timeline to the old one. Your different choices in a parallel life are not playing out in a disconnected void. They might be just a microscopic wormhole away, a hidden tunnel in the quantum foam linking your story to the one you did not live. This idea offers a potential path to the holy grail of physics, a theory of quantum gravity. Gravity, in Einstein's general relativity, is the curvature of spacetime. The ER=EPR conjecture suggests that quantum entanglement is not just a phenomenon within spacetime. It is what creates the very geometry of spacetime. The fabric of the universe, its smooth, continuous structure, emerges from a vast network of these quantum threads. It is a vision where the largest cosmic forces and the smallest quantum mysteries are two sides of the same coin, woven together by an infinite number of tiny bridges in the dark. Perhaps the most intimate connection between mind and cosmos lies deep within the fabric of our own brains. Roger Penrose, a Nobel Prize-winning physicist, and Stuart Hameroff, an anesthesiologist, proposed a theory so controversial it places consciousness itself at the heart of quantum mechanics. Their theory, called orchestrated objective reduction, or ORCH for short, suggests that the collapse of the wave function is not random, nor is it caused by simple observation. It is a physical process triggered by gravity, and it happens constantly inside the neurons of our brains. Penrose argued that a quantum superposition, like a particle being in two places at once, is inherently unstable. It creates a tiny, separate curvature in spacetime. This minuscule gravitational difference cannot be sustained for long. The superposition eventually collapses under its own weight, and the moment of that collapse is a fundamental moment of reality coming into focus. But where does this happen in a way that could produce a conscious thought? Hameroff pointed to structures inside our brain cells called microtubules. These are tiny, cylindrical scaffolds that help maintain the cell's structure. Orch proposes that these microtubules are the perfect environment to protect delicate quantum states. Within them, proteins could be in a superposition, performing a quantum computation. This process is orchestrated by the brain's biological functions, and when the gravitational instability reaches a threshold, the superposition collapses. Each collapse is a discrete event, a flicker of conscious awareness. In this view, your stream of consciousness is not a continuous flow. It is a series of these tiny quantum collapses, each one selecting a single reality from a sea of possibilities. This theory makes the staggering claim that our conscious observation does not just passively record reality. It actively participates in its creation through a gravitationally driven process inside our heads. The timeline you experience is the one your brain's quantum machinery has selected. Critics argue fiercely that the warm, wet environment of the brain is far too chaotic to support delicate quantum superpositions, which we usually only see in pristine, isolated labs cooled to near absolute zero. They say any quantum coherence would be instantly destroyed by decoherence. Yet, if Orch is correct, it forges an unbreakable link between the quantum world and the mind. It suggests the universe evolved consciousness not as an accident, but as a means to resolve its own quantum ambiguities. We are not just observers of the cosmos. We are the instruments through which the universe makes itself concrete, one conscious moment at a time. The stark simplicity of a cosmos split into two fundamental halves offers a compelling alternative to the infinite multiverse. This is the biverse theory, a vision of reality built on a profound symmetry, where the entire cosmos is mirrored by just one other, all-encompassing timeline. Instead of an endless tree of branching possibilities, we have a universe and its perfect twin. One dominant idea suggests these two worlds could be a matter universe like our own and an antimatter universe. In our reality, matter won out over antimatter in the early cosmos. But in the biverse model, this victory was not absolute. The initial symmetry of the Big Bang was preserved by creating two separate realms, one for each. Our world is built from matter, while the other is built from antimatter, a perfect mirror image where the roles are reversed. Another possibility is a universe of time flowing in opposite directions. From our perspective, our twin is contracting, its arrow of time pointing toward a big crunch, while ours expands toward heat death. Yet from their viewpoint, they are the ones expanding into the future, and we are the ones collapsing into the past. This elegant duality could solve one of cosmology's great puzzles, like why our universe appears so finely tuned for existence. The delicate balance might be a necessary consequence of this cosmic mirroring, where the properties of our universe are perfectly counterbalanced by its twin. Quantum mechanics provides a potential bridge between these two fundamental branches. The phenomenon of quantum tunneling, where a particle can seemingly pass through an impassable energy barrier, might not be a random jump. It could be a momentary connection, a brief gateway where information or influence leaks from one half of the biverse to the other. This creates a cosmic dialogue, a constant, subtle interaction that maintains the equilibrium of the whole system. We are not isolated in our single timeline. We are one half of a conversation, our reality forever intertwined with its one and only counterpart in the dark. Our experience of a smooth, flowing reality might be a grand illusion, a continuous fabric woven from countless individual threads. Causal set theory proposes that spacetime itself is not a seamless continuum, but is fundamentally discrete, built from a vast collection of simple, indivisible events. Think of the entire history of the universe not as a movie, but as a colossal, cosmic dot-to-dot puzzle. Each dot is a fundamental event, a point in existence, and the lines connecting them represent the causal relationships. One event must come before another if it can influence it. This entire structure, the collection of dots and their connecting lines, is called a causal set. The smooth, four-dimensional spacetime of Einstein's relativity emerges from this underlying, grainy reality when we zoom out. Much like a digital photograph appears smooth and continuous until you pixel peep and see the individual squares of color. The growth of this universe happens in a profoundly simple way. New events are born one by one, and they must find their place within the existing web of causality. Each new dot is linked to some past events becoming their future, but it remains completely unrelated to other events happening elsewhere in the set. This process of growth is where the magic of quantum possibility enters. The theory suggests that there is no single, predetermined way for the set to grow. When a new event is added, there are multiple, equally valid positions it could occupy within the causal structure. Each possible placement represents a different potential future. This provides a concrete, discrete foundation for the branching timelines we have explored. The continuous quantum probabilities we talk about are, at the most fundamental level, the result of this step-by-step, random growth of the causal set. Our seemingly smooth and deterministic timeline is just one possible path this cosmic assembly has taken. With every new event that comes into existence, the universe is faced with a choice, and each choice spawns a new branch in the tree of reality, all built from the bottom up, one discrete quantum of causality at a time. A single electron does not travel from point A to point B along a single, neat line. It takes every conceivable route at once. This is the heart of Richard Feynman's sum over history's approach, a revolutionary way of seeing the quantum world. He showed that to predict where a particle will end up, you cannot just consider one path. You must add up the contributions from every single possible trajectory, no matter how bizarre. It could take a direct route, a wild detour to the moon and back, or a zigzagging path that seems utterly nonsensical. Each path has its own probability, a kind of quantum vote. The final destination we observe is not the one true path. It is the combined effect, the average, of all these ghostly journeys interfering with each other. Now take this stunning idea and expand it to the scale of the entire cosmos. This gives us the multiverse of quantum histories. It suggests that our universe's entire timeline, from the Big Bang to this very moment, is not the only story that was ever written. Every possible history that could have logically unfolded is real. Every choice not made, every accident that did not happen, every alternate outcome of every quantum event, all of these histories exist as part of the grand quantum state of the cosmos. In one history, you became an astronaut. In another, the Roman Empire never fell. In a third, the laws of physics themselves are completely different. Our reality, the one we are living in right now, is not special or unique. It is simply the most likely average, the most robust combination of all these infinite paths. It is the loudest signal that emerges from the cosmic static of all that could have been. Think of a vast orchestra where every musician is playing a slightly different version of the same symphony at the same time. The cacophony is immense, but your ear is tuned to pick out the dominant melody, the one that arises from the collective harmony and dissonance. That melody is our experienced timeline. All the other notes are still there, contributing to the overall sound, but we only consciously perceive the central tune. This means your life is not a solitary thread. It is woven into a fabric of unimaginable richness, its stability dependent on the constant, silent hum of every path you did not take. So the next time you make a decision, remember that all the other choices are still out there, vibrating in the quantum background, each one a vital part of the cosmic equation that makes you you. The violent birth of our universe might not have been a singular explosion, but a quiet collision in the dark. The ekpyrotic and cyclic models propose a radically different origin story, one where the Big Bang was not the absolute beginning. In this vision, our entire three-dimensional universe is a membrane or a brain, floating within a higher dimensional reality called the bulk. We are like a single, impossibly vast sheet of paper drifting in a multidimensional void. And we are not alone. Another brain, a parallel universe, floats nearby. The Big Bang in this model was the moment our brain collided with that other one. This was not a catastrophic crash of planets and stars, but a transfer of energy so immense it ignited the hot, dense state from which our cosmos expanded. This single event sets the stage for a much grander cycle. After the collision, the two brains move apart, stretched and energized by the impact. But the mysterious force that connects them, a kind of spring-like attraction, eventually pulls them back together. They collide again and again in an endless cosmic dance. Each collision creates a new universe from the ashes of the old one, a new Big Bang that starts the cycle over. This is a universe without a true beginning or end, only an eternal rhythm of creation and destruction. Within each cycle, the quantum fluctuations that seed galaxies are subtly different. The random dice rolls of quantum mechanics do not repeat perfectly each time. This means every new universe in the cycle could have a slightly different history. In one cycle, the quantum seeds might produce more galaxies. In the next, they might produce fewer. This creates a series of distinct quantum timelines, not a single, linear history, but a succession of universes, each with its own unique story. One cycle might give rise to a timeline where life is common, while the next might create a cold, empty cosmos. Our reality is not one branch on an infinite tree, but one verse in an endless cyclical song, each chorus sung with a slightly different tune. The very fabric of our cosmos might be the interior of a collapsed star from a grander parent universe. Black hole cosmology presents this startling possibility, suggesting our entire expanding universe, with all its galaxies and history, is contained within the event horizon of a black hole existing in a higher dimensional reality. This idea emerges from a fascinating mathematical similarity. The equations describing the singularity of a black hole, a point of infinite density, bear a striking resemblance to those describing the Big Bang. It is as if the birth of our universe mirrors the death of a star in a cosmos beyond our own. This leads to a profound and natural multiverse. In the parent universe, countless black holes form from dying stars. According to this theory, each one does not lead to a dead-end singularity, but to a new, burgeoning cosmos within. Every black hole is a potential Big Bang, a portal to a new space-time with its own unique laws and initial conditions. Your entire life, from the air you breathe to the light from distant stars, could be unfolding inside the remnant of a stellar cataclysm that occurred in a reality we can never see. This creates an infinite regress of nested universes, a cosmic matryoshka doll where each layer contains the seeds for the next. What happens to the quantum information that falls into a black hole in the parent universe? This is the famous black hole information paradox, and this cosmology offers a radical solution. The information is not lost or destroyed. It is translated, becoming the initial conditions, the quantum fluctuations that shape the newborn universe inside. The specific pattern of matter and energy that fell into the parent black hole could dictate the fundamental constants and the distribution of galaxies in its child universe. The history of one cosmos becomes the raw material for the next. This means the quantum timeline we experience, with all its specific events and branching possibilities, might be a direct inheritance, a complex transformation of information from a universe that came before ours. We are not just living in a black hole, we are living its story, a cosmic tale rewritten into a new form, forever separated from its source by an impenetrable veil of space-time. But what if the universe never splits at all? The many minds interpretation takes the strangeness of quantum mechanics and turns it inward, suggesting the branching happens not in the cosmos but within your own consciousness. This theory accepts the same mathematical foundation as the many worlds view, where all possible outcomes of a quantum event physically occur. The crucial difference lies in what we believe is splitting. Instead of an infinite number of parallel universes, there is only one single, constantly evolving universal wave function. The multiplicity is not out there in the world. It is in here, in the mind of every observer. When you witness a quantum event like the decay of an atom, your brain enters a superposition of states. One version of your mind perceives the atom decaying, while another, equally real version of your mind perceives it as stable. Both experiences are real, but they are separated into different, non-communicating streams of awareness within a single physical brain. Think of your consciousness not as a single light beam, but as a prism that splits a beam into its component colors. The white light is the totality of your potential experiences, and each color is a separate, subjective timeline you're living through simultaneously, yet completely unaware of the others. This offers a starkly personal solution to the measurement problem. There is no mysterious collapse because every possible outcome is always realized. The question of which outcome you see is answered by which mental branch your awareness happens to follow in that moment. This means the quantum timeline you experience is not a shared, objective history. It is a deeply private narrative, one thread of experience woven from the vast tapestry of your own mind. You are not living in one universe among many. You are living many universes within one mind. This leads to a profound and isolating philosophical conclusion. The person standing next to you, who seems to share your reality, might actually be experiencing a completely different outcome of the same quantum event, their consciousness following a different branch within their own mind. We are all alone in a shared physical world, each of us navigating a private multiverse of our own making. Your personal experience is the ultimate quantum reality. This is the radical proposition of quantum Bayesianism, or cubism for short. This interpretation flips everything we have discussed on its head. It declares that quantum probabilities are not objective features of the world. They are not out there waiting to be discovered in a multiverse or collapsed by an observer. Instead, they are entirely subjective. They represent your own personal degrees of belief, your best guess about what will happen in a future interaction with the world. For a cubist, the quantum state is not a description of a system. It is a user manual, a personal guidebook that you, the agent, create and constantly update based on your experiences. Imagine you are about to meet a friend for coffee, but they are often late. You might assign a 60% probability that they will be on time based on your past history with them. This is not a fact about the universe. It is your own internal bet, your subjective confidence level. Cubism applies this exact same logic to the core of quantum mechanics. When a physicist says an electron has a 50% chance of spinning up, a cubist would say that number simply reflects the physicist's own uncertainty. It is the physicist's personal betting odds on what they will see when they run the experiment. This completely redefines the nature of our timeline. There is no single, true history of the universe that is objectively real. Instead, each one of us is constantly constructing our own personal narrative of reality. Your timeline is a unique story shaped by the sequence of interactions you have with the world and the expectations you form from them. Every measurement you make is not revealing a hidden truth. It is a moment where you update your internal guidebook, refining your beliefs for the next encounter. quantum mechanics in this view is not a theory about what the world is. It is a tool for navigating a world that is fundamentally uncertain and personal. It is a framework for making better decisions when you cannot know everything. This makes the cosmos a deeply participatory place, but not in the way the participatory anthropic principle suggested. You are not summoning reality into being for everyone. You are writing your own private user manual for a universe that remains forever mysterious and unique to you. The solid world we all seem to share is then a magnificent consensus, a rough agreement between countless individuals all updating their own personal quantum guidebooks. This controversial idea suggests the quantum dice are loaded from the very start. Superdeterminism argues that the apparent randomness we observe is a complete illusion, a trick of perspective. In this view, every single event, from the path of an electron to the decision of a scientist to run an experiment, was locked into place at the moment of the Big Bang. The universe is a single, unbroken chain of cause and effect, with no room for chance or alternative possibilities. This theory directly confronts the famous spooky action at a distance of quantum entanglement, where two particles instantly influence each other. Superdeterminism explains this not as a mysterious connection, but as a consequence of a shared, predetermined past. The particles are not communicating faster than light. They are simply behaving according to a script written at the dawn of time, a script that includes the exact moment and method of their measurement. Our choices feel free, but they are simply the unfolding of a cosmic code set in motion billions of years ago. This eliminates the need for infinite branching timelines because there is only one possible path the universe can take. It offers a clean, local, and deterministic account of quantum phenomena, solving puzzles that have baffled physicists for a century. Yet the cost of this elegant solution is staggering. It fundamentally dismisses the concept of free will as a comforting story we tell ourselves. Your life, with all its seeming choices and accidents, was preordained by the initial state of the cosmos. You are always going to watch this video, and these words were always destined to be spoken in the one and only timeline that ever truly existed. The future might already be whispering secrets to the past. Retrocausality models dare to suggest that time's arrow is not a one-way street, and that events yet to come can reach back and shape what we perceive as history. This is not time travel in the science fiction sense, but a fundamental reworking of cause and effect within the quantum realm. The most compelling evidence comes from a mind-bending experiment known as the delayed choice quantum eraser. In this setup, a single photon is fired toward a screen, but first it encounters a beam splitter, a device that gives it a choice of two paths. The photon's behavior is a quantum riddle. Does it act like a particle, taking one definite path, or like a wave, taking both paths at once and interfering with itself? The answer depends on how we choose to measure it, but the twist is that this choice can be made after the photon has already finished its journey and hit the detector. It is as if our decision in the present reaches back in time to retroactively determine what the photon was doing in the past. If we choose to measure which path it took, the photon will have always been a particle. If we choose to erase that path information, the photon will have always been a wave. The future measurement appears to dictate the past behavior. How can this be? Retrocausality proposes that the timeline is not a sequence of causes leading to effects, but a single, self-consistent loop. The final outcome and the initial setup are entangled from the start, working in concert to produce one coherent story. Think of a novelist who writes the final chapter first, then goes back to write the opening, carefully seeding clues that make the ending feel inevitable. The beginning is written with the end already in mind. In the quantum world, the entire event is that complete novel. The moment of measurement in the future is not causing something in the past. Instead, the past and the future are mutually defining, locked in a dance that creates a seamless, singular reality. This offers an elegant alternative to the endless branching of the multiverse. There is no need for infinite parallel worlds to account for every quantum possibility because there is only one timeline. That single timeline, however, is not fixed and linear. It is a flexible, interdependent whole where what we call the future helps to weave the very fabric of what we remember as the past. The universe ensures everything fits together in a perfectly consistent way, with the future acting as a guiding hand, pulling the threads of possibility into one unbroken thread of reality. The solidity of spacetime may be the grandest illusion of all. The emergent spacetime hypothesis proposes that the four-dimensional universe we inhabit, with its seamless fabric of space and time, is not a fundamental stage. It is a secondary phenomenon, a collective behavior that arises from something far more basic, a seething ocean of quantum information. Think of a perfectly smooth sheet of ice. It seems like a continuous, solid plane, but we know it is actually made of trillions of individual water molecules locked in a vibrating lattice. The property of smoothness does not exist in any single molecule. It only appears when we consider the vast ensemble together. In the same way, the smooth, continuous geometry of spacetime might emerge from a vast network of interconnected quantum bits or qubits. These are not tiny particles in space. They are the fundamental constituents, and their relationships, their entanglements, literally weave the fabric of space and time itself. Without this underlying network, there is no here, there, or when. This turns our understanding of reality inside out. The flow of time, that relentless forward march we all experience, may not be a fundamental feature of the cosmos. It could be an emergent property, much like the temperature of a gas emerges from the frantic, random motion of its molecules. No single molecule has a temperature. Temperature is a collective statistic. Similarly, the arrow of time might be a statistical trend arising from the way quantum information becomes increasingly scrambled and complex across the entire network. This directly reframes the nature of quantum timelines. If space and time are not the bedrock of reality, then the branching of timelines is not a splitting of the cosmos itself. It is a reorganization of the underlying quantum information. Each potential outcome in a quantum experiment represents a different possible configuration of the network. What we perceive as a new, parallel universe branching off is simply the information entangling in a new pattern, creating a new set of relationships that, from our emergent perspective, looks like a separate spacetime. Your life is not a path through a pre-existing landscape. You are part of the landscape itself, a dynamic pattern in a cosmic computation that is constantly rewriting its own geometry. This suggests that at the most fundamental level, there are no timelines, only quantum states. The past and future are not out there somewhere. They are potential patterns in the data, and our conscious present is the moment where one specific pattern achieves stability, casting the illusion of a single, flowing reality. The very geometry of space itself might be an evolving network of quantum links. This is the radical proposal of quantum gravity, a theory that suggests our smooth, continuous universe began as a chaotic, hyper-connected web. Picture the infant cosmos not as a tiny, dense point, but as a graph, a vast collection of points where every single point is connected to every other point. In this primordial state, there are no notions of distance or direction, just an undifferentiated tangle of pure connection. At these unimaginable energies, the structure of space is not fixed. It is a fluid quantum system, and its connections can exist in a superposition. Each possible configuration of this cosmic graph represents a different geometry for spacetime, a different potential reality. These are the raw, unformed blueprints for every possible quantum timeline, all existing simultaneously in a state of turbulent potential. As the universe expanded and cooled, this graph underwent a phase transition, much like water freezing into ice. The infinite, unstable connections began to snap, leaving behind a stable, orderly lattice. the points that remained linked became the nearest neighbors in our three-dimensional space, defining the very concept of distance for the first time. The countless other superpositions of connection, the ghostly architectures of other timelines, were frozen out, becoming the unobservable background of our cosmos. Our smooth, classical spacetime is the crystal that formed from this quantum soup, a single, stable pattern selected from an infinite number of possibilities. The timeline we experience is not a path through a pre-existing landscape. It is the final, frozen geometry of a graph that chose one way to connect, locking our history into a single, coherent shape. Perhaps the universe itself is awake. This is the profound and ancient idea of panpsychism, a philosophy that suggests consciousness is not a rare accident born from complex brains. Instead, it is a fundamental and ubiquitous feature of reality, as basic as space, time, and matter. In this view, everything possesses some form of inner experience, a faint spark of subjective feeling. A rock has a minimal, primitive consciousness, a planet has a vast, slow, geological awareness, and a human being has a rich and complex inner life, all part of the same spectrum. This is not to say a rock thinks or feels pain as we do. Its experience would be unimaginably simple, perhaps just a bare, raw awareness of existing. But if consciousness is truly fundamental, then it was present at the very dawn of the cosmos, woven into the fabric of the Big Bang itself. This leads to a stunning possibility for our quantum timelines. We have seen how the universe seems to exist as a blur of possibilities until an observation forces it to choose a single state. But what is doing the choosing? The Copenhagen Interpretation points to a vague act of measurement. Panpsychism offers a much more definite answer. The fundamental consciousness present in every particle, in every quantum field, is what resolves the superposition. Each tiny spark of awareness, in its own simple way, is making a choice, collapsing the wave function from the bottom up. The solid reality we experience is not built by human observation alone. It is the collective result of trillions upon trillions of conscious choices made at the quantum level every instant. Our own human consciousness, then, is not the sole author of reality. It is a concentrated, emergent expression of a quality that permeates the entire cosmos. We are not observers looking in at a separate universe. We are the universe becoming aware of itself, a localized node where the cosmos can reflect upon its own existence. This creates a universe where mind and quantum potentiality are inextricably linked, a single, conscious entity perpetually dreaming itself into being, one definite moment at a time. The quest to unify the cosmos leads us to the ultimate goal of physics, a final theory of everything. This grand framework, whether it emerges from the vibrating strings of string theory or the woven loops of loop quantum gravity, promises to answer the most profound question haunting our journey. Are the infinite quantum timelines we have explored a genuine, physical reality, or are they merely a mathematical artifact, a useful trick in our equations? A successful theory of quantum gravity would settle this debate once and for all. It would reveal the true architecture of spacetime at the smallest possible scale, the Planck length. In loop quantum gravity, reality is a fabric woven from individual threads of space, a spin network. The evolution of this network creates the flow of time we experience. In this picture, the branching of timelines might correspond to actual points where the network itself splits, creating new, distinct patterns in the geometry of reality. String theory, with its holographic landscapes, suggests a different resolution. All possible timelines could be encoded simultaneously on a distant boundary, with our experienced reality being just one projection from that cosmic data set. The hope is that a verified theory of everything would not just describe one universe, but provide a single, elegant equation that encompasses all possible universes and their histories. It would show us how the quantum fuzziness of the small scale seamlessly stitches together into the smooth, curved spacetime of general relativity. Such a theory would be the great unifier, weaving together the many worlds and Copenhagen views, the transactional handshakes and the emergent spacetime, into one coherent and breathtaking picture. It would tell us if our choices truly spawn new worlds, or if they simply follow a single, predetermined path through a block universe. We would finally know if we are living in one universe among an infinite chorus, or if we are the sole, singular verse in an incomprehensible song. The final theory would be the key that unlocks the deepest nature of existence itself, revealing whether our reality is a solitary thread or an infinite tapestry. Our deepest theories may not be a final picture, but merely the closest approximation our minds can construct. This brings us to the 30th and final theory, a profound frontier defined by the limits of knowledge itself. The unsettling possibility is that quantum mechanics is fundamentally incomplete, not because our models are flawed, but because reality possesses aspects that are forever beyond the reach of any observation or theory. There could be a ceiling to human understanding, a horizon we can approach but never cross. The bizarre rules of quantum mechanics, with their probabilities and superpositions, might not be the ultimate laws. They could be the shadows cast by a deeper, hidden reality that operates on principles we cannot access, a realm of pure potential that our mathematics can only crudely approximate. This idea finds a powerful echo in Kurt Gödel's incompleteness theorems, which mathematically prove that any sufficiently complex logical system will contain true statements that cannot be proven within that system. Our quest for a theory of everything might be like a fish trying to formulate a theory of water. It can describe the currents and the pressure, but it can never grasp the concept of wetness. If this is true, then the true nature of quantum timelines, whether they are a branching multiverse or a single, convoluted path, might be one of those unprovable truths. We are left with a necessary humility. Our most brilliant models, from the block universe to the holographic principle, are not reality itself. They are maps, and the map is never the territory. The infinite tapestry of existence may be woven from a thread so fine that our instruments, and perhaps our very consciousness, are too coarse to perceive it directly. The ultimate answer to the mystery of our timeline might not be a revelation waiting for a smarter physicist, but a silent, eternal question mark at the heart of the cosmos. We have traveled through a constellation of 30 extraordinary theories, each one a brilliant attempt to map the uncharted territories of existence. From the infinite branching worlds of Everett to the ghostly cat of Schrödinger, from the cosmic hologram to the conscious universe of panpsychism, we have seen reality refracted through countless lenses. These are not just abstract ideas, they are profound responses to the fundamental human yearning to understand our place in the cosmos, to answer why there is something rather than nothing, and to decipher the true nature of time, consciousness, and the fabric of space itself. This journey reveals that our universe, in all its manifestations, is infinitely stranger and more magnificent than our everyday perceptions allow us to see. The very act of questioning, of exploring these radical possibilities, expands the boundaries of what we consider real. So we turn the final question over to you. Which of these 30 visions of reality resonates most deeply with your own sense of wonder? Does the deterministic clockwork of superdeterminism feel right, or does the participatory power of the anthropic principle call to you? Share your thoughts in the comments below. Your perspective is now part of this ongoing cosmic conversation. And if you are ready to continue unraveling the mysteries of existence, be sure to subscribe for more deep dives into the wonders that lie just beyond the edge of our understanding.